Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Transferred Electron Devices Gunn Diode from the paper Electronics. So students, let us see what we are going to learn in this module. First, we will discuss about the negative differential resistance. Second, a two-valley model which is used to describe the NDR, negative differential resistance. Thirdly, the detailed description about the semiconductor exhibiting the NDR. Then we will discuss about the transferred electron device along with its IV characteristics and working. So students, let us start with a basic introduction about the module. It was first observed in 1963. A microwave output was generated when a DC field greater than the critical threshold value of several 1000 volts per centimeter was applied across a short, very thin active region, N-type gallium arsenide as indium phosphide, cadmium telluride. It utilizes a voltage-controlled differential negative resistance DNR. So, this phenomenon that gives rise to DNR is the decrease in the electron mobility with the electric field. This decrease is caused by the transfer of conduction of electrons from a high mobility, low energy state to a low mobility, high energy state under the action of high zeta greater than few kilovolts per centimeter. This transfer is made possible by the peculiar band structure of semiconductors like gallium arsenide and indium phosphide. Cadmium telluride is used as the local oscillator and power amplifier 1 to 100 GHz. This implies that Vn is equal to minus q tau c by Mn multiplied by zeta, where μn is equal to q tau c by Mn is the carrier transport parameter, implies that how strongly the motion of an electron is influenced by the applied zeta, and here Vn is equal to minus mu n zeta. So here we assume that tau c is independent of zeta and is reasonable as long as Vd is small compared to the thermal velocity Vt of the carrier. As Vd is greater than Vt, the field dependence on zeta will begin to depart from the linear relationship as shown in this figure. So for N-type gallium arsenide, Vd reaches the maximum and then shows a decrease with increase in zeta. This phenomenon is due to this implies that Vn is equal to minus q tau c by Mn multiplied by zeta, where μn is equal to q tau c by Mn is the carrier transport parameter, implies that how strongly the motion of an electron is influenced by the applied zeta, and here Vn is equal to minus mu n zeta. So here we assume that tau c is independent of zeta and is reasonable as long as Vd is small compared to the thermal velocity Vt of the carrier. As Vd is greater than Vt, the field dependence on zeta will begin to depart from the linear relationship as shown in this figure. So for N-type gallium arsenide, Vd reaches the maximum and then shows a decrease with increase in zeta. This phenomenon is due to the energy band structure of gallium arsenide. The band structure of gallium arsenide allows the transfer of conduction electrons from a high mobility energy minimum called a valley, valley 1, to low mobility higher energy satellite valleys. Consider a E-P bar diagram of gallium arsenide conduction band as shown in this figure, that is two valley model. Free electrons kinetic energy E is equal to P square by 2 m naught, where P is the particle momentum and m naught is the free electron mass. So because of periodic potential of nuclei, effective mass of the conduction electron Mn is different from the mass of free electron Me. Therefore, for conduction electron, E is equal to P bar square by 2Mn, where P bar is the crystal momentum. So maximum in the valence band at P bar equal to 0, minimum in conduction band at P bar equal to 0. Therefore, transmission valence band approaches the conduction band can occur without any change in the P bar value, the only change in E required. Therefore, gallium arsenide is a direct band gap semiconductor. The E-P bar relation near conduction band minimum or near valence band maximum are parabolic, that is E equal to P bar square by 2Mn. From known E-P bar relation, we can obtain the effective mass as Mn equal to d square E by dP bar square to the power minus 1. So this implied that narrower the parabola, smaller the effective mass. Therefore, very narrow conduction band parabola for lower value of gallium arsenide, the electron effective mass is small, approximately 0.07 m naught. However, satellite valley, the upper valley as shown in the figure, has higher effective mass due to wider conduction band parabola. So the two valley model has the following features. Number 1, the sharp curvature of conduction band, lowest minimum at P bar equal to 0, lower valley, that is valley 1. So therefore, the electrons in valley 1 have low effective mass m1, implying high mobility mu1. Another energy minimum in conduction band along 111 occurs, that is satellite valley, valley 2, which is separated from valley 1 by energy delta E equal to 0.31 electron volt. So the curvature of valley 2 is broader. The electron effective mass Me is high, implying low mobility mu2. The second feature is that the density of states in satellite valley is higher than that in the lowest valley. So here the third feature is that the delta E is greater than kT, the thermal energy of electrons at RT. Therefore, lattice temperature must be low. This implies the transfer of electrons from valley 1 to valley 2 by thermal agitation is not very likely. Also, delta E is less than Eg. Electrons transfer can occur at zeta, much lower than those required for avalanche breakdown. Let N1 and N2 be the electron density in valley 1 and valley 2 respectively. The steady state conductivity of N-type gallium arsenide is sigma equal to Q mu1 M1 plus mu2 N2 equal to Qn mu bar or Qn mu by zeta. Now here N1 plus N2 is your N. We have replaced N1 plus N2 by N square and N equal to capital ND and mu bar is Vn by zeta. It's average mobility where Vn is the average drift velocity. So here mu is mu1 m1 plus mu2 n2 by n1 plus n2, and n is n1 plus n2, and your Vn is mu bar zeta. So if the field is low, that is zeta is less than zeta A, all conduction electrons, they are located in valley 1. As zeta increases, some electrons gain sufficient energies from zeta and they make a transition to satellite valley, valley 2. If zeta is high enough, all the conduction electrons, they transfer to valley 2, that is n1 equal to n and n2 equal to 0. And here zeta is varying from 0 to zeta A, n1 plus n2 equal to n, for zeta varying from zeta A to zeta B, and n1 is equal to 0 and n2 equal to n for zeta B, for zeta greater than zeta B. So using the previous equations, equation 3 and equation 4, the effective drift velocity will be Vn equal to mu1 zeta for valley 1, that is zeta varying from 0 to zeta A, and Vn equal to mu2 zeta for valley 2, that is zeta B is less than zeta, and Vn equal to mu1 n1 plus mu2 n2 by n1 plus n2 multiplied by zeta for zeta varying from zeta A to zeta B, that is both valley 1 and valley 2. So if mu1 zeta A is greater than mu2 zeta B, there exists a region where drift velocity decreases with increasing field between zeta A and zeta B. Thus differential mobility mu is del Vn by del zeta less than 0. In NDR, if zeta is greater than zeta t, where zeta t is 3.5 kilovolts per centimeter for gallium arsenide. So the current density J equal to sigma E using equation 1 and equation 4, and J is equal to Qn mu1 zeta for zeta varying from 0 to zeta A, and J equal to Qn mu2 zeta for zeta B greater than zeta as shown in this figure. If mu1 zeta A is greater than mu2 zeta B, which implies the negative differential resistance exists, zeta T implies the onset of NDR, that is the threshold field as shown in this figure. Zeta V here is the valley field. NDR is the region between the zeta T and zeta V. This implies the differential conductivity sigma T equal to dJ by d zeta less than 0 in NDR. So a semiconductor exhibiting the negative differential region NDR is inherently unstable because a random fluctuation of carrier density at any point in the semiconductor produces a momentary space charge that will grow exponentially with time. So the 1D continuity equation is del n by delta t minus 1 by q del j by del x equal to 0. If there is a small local fluctuation of majority carriers from the uniform equilibrium concentration, the locally created space charge density is n minus n naught. So Poisson's equation and current density are del zeta by del x equal to minus q n minus n naught by epsilon s, and j equal to zeta by rho plus q d delta n by del x. So here nxt is the electron concentration at any point x and time t. And here epsilon s is the dielectric permittivity, rho is the resistivity, and d is the diffusion constant. Differentiating equation 3 with respect to x, del J by del X equal to 1 by rho delta sigma by delta X plus QD del square N by del X square. This implies 1 by Q del J by del X equal to minus N minus A naught by rho epsilon S plus D del square N by del X square. So now substituting equation 4 and equation 1 and J equal to Qn V bar E, where J is constant, with X and nu equal to nu E, then we get delta N by delta T plus N minus N naught by rho epsilon S minus D del square N by del X square equal to 0. So this equation can be solved for both spatial response or temporal response by the separation of variables, that is, let nxt equal to n1x n2t. So for special response, the solution is given by n minus n naught equal to n minus n naught at x equal to 0 multiplied by e to the power minus x by LD, where LD is the Debye length given by LD equal to root of kt epsilon s by q square n naught. Now here LD is the distance over which a small unbalanced charge decays. For the temporal response, the solution of equation 5 is given by n minus n naught equal to n minus n naught at t equal to 0 e to the power minus t by tau r, where tau r is the dielectric relaxation time or the Maxwell differential dielectric relaxation time given by tau r equal to rho epsilon s equal to epsilon s by q mu bar n is equal to epsilon s by q mu bar n naught, where mu bar is the average mobility. So tau r is the time constant for the decay of space charge to neutrality if the differential resistivity is positive. So tau r is 10 to the power minus 10 to 10 to the power minus 11 seconds for gallium arsenide. For epsilon s equal to 12.8 epsilon naught, mu bar equal to 8500 centimeters square by nu s, and not equal to 10 to the power 15 centimeter minus 3. However, if semiconductor exhibits the NDM, any charge imbalance will grow with time constant tau r instead of the decay, as shown in this figure. The positive differential resistivity increases with increase in zeta, that is del rho by del zeta is greater than 0. So if a region has slightly higher field, the resistance there is larger. This implies less current will flow through it, results in an elongation of the region, and a high field domain is formed separating the regions of low field. The interface separating the low and the high field domain lie along the equipotentials so that they are in planes perpendicular to the current direction as shown in this figure. Equation 8 implies that for a device with NDR, initial space charge increases with time, which was given by equation 9, where mu is the negative differential mobility. So if equation 8 remains valid throughout the entire transition time of space charge layer, the maximum growth factor would be exponential VSR, that is multiplied by L, where L is the device length, Vs is the drift velocity, average drift velocity of space charge layer. So for large space charge layer, LV by tau r is greater than 1. So that is N naught multiplied by L is greater than epsilon s Vs q mu. That is from equation 9. So the simplest form of space charge instability is the accumulation layer. So lightly doped or short samples, that is N naught multiplied by L, is less than 10 to the power centimeter minus 2, exhibits a stable field distribution when a constant voltage is applied. So in a device with N naught L greater than 10 to the power 12 centimeter minus 2, a traveling accumulation layer will be formed. The NDR may lead to the growth of small fluctuations in the space charge in a sample. So an equivalent circuit is shown in this figure, where differential resistance RD is equal to L by sigma area equal to L by Qn naught mu bar S, and differential capacitance CD equal to epsilon S by L, which implies the RC time constant, and tau R is RDCD equal to epsilon S by Q mu N naught mu bar. This is also known as Maxwell differential dielectric relaxation time. So in a material with a positive differential conductivity, a space charge fluctuation decays exponentially with time, as equation 8, where n minus n naught at t equal to 0 is a fluctuation magnitude at t equal to 0. So when differential conductivity is negative, the space charge fluctuation may actually grow with time. So consider a transferred electron device as shown in this figure, made up of n-type gallium arsenide with n plus end contacts. Let at point A in the device there exist an excess or accumulation of negative charge that could be due to a random noise fluctuation or possibly a permanent non-uniformity in doping, shown in figure C. So integration of Poisson's equation gives zeta distribution, figure D, where zeta on the left of A is less than zeta on the right of A. If a device biased at zeta A, figure A, carriers flowing into the point A are greater than the carriers flowing out of A. So electrons flowing in left A are in low zeta and hence higher velocity. So on the right, in high zeta, the velocity is low. Electrons accumulate at the boundary, that is notch, causing large discontinuity in zeta, and velocity becomes more different in two regions. This increases the excess negative space charge at A. Accumulation of electrons continues. Since J is constant throughout the device, an increase in n at point A causes Vn drift velocity to decrease. Therefore, electrons in this region, they are slower down and causes increase in the negative charge. So now the field to the left of the point A is even less than it was originally, and the field up to the right is the space charge accumulation. So the process continues until the low fields and high fields both obtain outside the NDR, and they are settled at zeta A and zeta B. So where current in the two regions are equal. So a traveling space charge accumulation layer is formed, which was discussed previously, and this process depends on the condition that the number of electrons inside the crystal be large enough to allow the necessary amount of space charge to build up during the transit time of space charge layer. So here the space charge increases exponentially with time and continues to until attains the maturity. So when collected at the anode, field rises above zeta t and new space charge is nucleated at the cathode. So cycle repeats itself and current oscillates in microwave. This is the simplest form of space charge instability. Now consider a practical transferred electron device as shown in the figure, When there are positive and negative charges separated by a small distance, a dipole domain is formed. So zeta inside the dipole is greater than zeta on either side. So because of NDR, first low field is greater than the I high field. So two field values will tend towards the equilibrium values outside the NDR region, where I low field equal to the I high field, as shown in this figure. So the diode has now reached a stable state and moves through the crystal and disappears at the anode. Here zeta begins to rise uniformly across the sample through zeta t, that is zeta is greater than zeta t, thus forming a new dipole, and the process repeats itself. So the applied potential V is capital V equal to zeta AL equal to zeta 2D plus zeta 1 L minus D, where L is the sample length and the dipole width is D equal to L multiplied by zeta A minus zeta 1 divided by zeta 2 minus zeta 1. The time required for the domain to travel from the cathode and anode is L by Vs, where L is the active device length and Vs is the average velocity. So the frequency for the transit time domain mode is F equal to Vs by L. Many Gunn diode oscillates at the frequency that is approximately 10 to the power 7 centimeter per second by L, equal to 100 gigahertz by L in micron. So therefore sample with L equal to 10 micron will oscillate at approximately 10 gigahertz. If L equal to 25 micron oscillates at approximately 4 gigahertz, the increase in the free electrons in one region causes decrease in its concentration in another region. Thus higher field for electrons in this region. So higher field will slow down these electrons relative to the other part due to NDR. Excess electrons will grow because the electrons in trailing part arrive with higher velocity for lower field than EA, and depleted electrons area also grow because electrons slightly ahead of this region with excess electrons can move faster. So this implies the perturbation. So as shown in this figure, the peaks will traverse across the Gunn point applied potential and growing as it transits the diode due to NDR. Now consider the device as shown in this figure. Let the applied field in the sample is greater than ET. So initially electric field and concentration distribution is uniform in the sample, and let the sample has a fluctuation of electron concentration. So as shown in this figure, this fluctuation can lead to an electric field fluctuation, that is delta zeta by delta x equal to minus q n minus n naught by epsilon s. So in the higher field region, the electrons slow down, and these slow electrons increases the original concentration fluctuation. So this fluctuation, so higher the field and low field with fluctuation, and hence velocity decreases continuously. This fluctuation develops in such a way that accumulation layer remains behind and the front edge is depleted with electrons. At the same time, the entire fluctuation drifts towards the positive contact, the anode, with the velocity of slow electrons, that is Vs. So if the sample is long enough, fluctuation develops into a high field domain. When the domain is moving between the cathode and the anode, the current at the device electrodes is IV equal to QNVS. However, when domain dissipates in the anode and new domain did not form, yet current at the device electrodes. So Im equal to Qn Vs, where Vm is greater than Vs, and Vm is the initial high current before activation of the fluctuations. So characteristic time of high field domain formation is tau r equal to RT CD equal to epsilon s by Q n naught mu, also known as Maxwell relaxation time, where mu is the differential electron mobility. Let us now discuss the Gunn diode mode of operations. Characteristic domain transit time in the sample of length L is tau Tr equal to L by Vs. So if domain formation time, that is tau r, is greater than domain transit time, then domain does not have enough time to develop and the diode is stable. So Gunn diode works as a stable amplifier. However, if Tr is less than Ttr, then Gunn diode may oscillate due to instabilities. So the Kromer criterion for domain formation is Ttr is greater than Tr, or L by Vs is greater than epsilon s by Q n naught mu. Therefore, n naught L is greater than epsilon s Vs by Q mu. So in general, the transit time for the domain travel is equal to 3 times Tr. Hence, the distance traveled by the domain in 3 times Tr time is LTTr equal to Vs multiplied by 3Tr. Therefore, length of the Gunn diode for instability is kept as L greater than 3 Vs Tr is greater than 3 epsilon s Vs by Q mu n naught. So when the sample meets Kromer criterion, a high field domain periodically develops at the cathode side, drifts towards the anode and dissolves there. So this implies always one domain propagating in the sample if the applied voltage is above the threshold and constant. So here the current with domain formation decreases and increases when the domain dissipates. So the oscillation frequency or the transit time frequency is Ft approximately 1 by tau Tr equal to Vs by L, and all these parameters are shown in this figure. For sample with L equal to 100 micron and for gallium arsenide Vs equal to 10 to the power 7 centimeters per second, this tau t will be equal to L by Vs, which is equal to 10 to the power minus 9 seconds after putting the value of L and Vs. So the frequency of transit time oscillations will be given by, that is for L equal to 10 micron and Ft equal to 10 gigahertz, we will get the Ft to be equal to 1 gigahertz. Therefore, operating frequency is controlled by the sample length. No tuning varies from sample to sample. It is sensitive to sample non-uniformities. So, current waveform consists of short pulses with the width less than half a period. So, students, let us summarize what we have learnt in this module. Firstly, we detailed description about negative differential resistance was discussed. Secondly, a two-valley model by taking examples from N-type gallium arsenide was discussed. Thirdly, the description about the semiconductors exhibiting the negative differential resistance, they were also discussed in detail. Lastly, we discussed about the important devices, that is transferred electron devices or Gunn diodes, along with their IV characteristics and working. Thank you.